All right, guys. In this video, we're going to talk about hypothesis test for population proportion. In the previous video, we learned we learned the hypothesis test procedures, just like how to set up the non-alternate hypothesis and what kind of possible outcomes we could get, and based on the possible outcome, how to make the conclusions. Basically, we went over all the procedures of hypothesis test. Now let's take a look at in this video. Let's take a look at how to do the hypothesis test for population proportion. Now, first of all, let's take a look at this example here. Pull out the marker. It says a researcher obtains a random sample of 1,000 people and finds that 533 are in favor of the banning cell phone use when driving. So the p hat would be equal to x over n, which is 534 divided by 1,000. This suggests that more than 50% of people favor the policy, or is it possible that the true proportion of registered voters who favor the policy is some proportion less than 0.5, and we just happen to serve a majority in favor of the policy? In other words, would it be unusual to obtain a sample proportion of 0.534 or higher from the population whose proportion is 0.5? What is convincing or statistically significant evidence? So to answer all those questions given in this example, we need to do the hypothesis test for population proportion. Now let's take a look at how to do it, and we're going to go back to this example later, and we're going to learn how to answer those questions by doing the hypothesis test. All right, since it says at the last, it says what is convincing or statistically significant evidence. Now let's take a look at what kind of evidence is statistically significant. When observed results are unlikely under the assumption that non-hypothesis is true, so we see the result is statistically significant. When results are found to be statistically significant, we reject the non-hypothesis. So basically, if we have a result that is statistically significant, then we're gonna reject non-hypothesis. That's what does it mean by saying that some results are statistically significant. All right, once this is clear, let's take a look at this. So to determine if a sample proportion of 0.534 is statistically significant, we build a probability model. Since NP times 1 minus P is equal to 250, which is greater than or equal to 10, and the sample size n is 1,000 is sufficiently smaller than the population size, we can use a normal model to describe the variability in p hat. Actually, we mentioned those two conditions. I'm sorry. So actually, I believe I mentioned those two conditions in chapter 7. I think 7.1. So in that section, I mentioned a little bit, just like technically we should check those two conditions and see if this NP times 1 minus P greater than or equal to 10 or not, or if the sample size is sufficiently smaller than the population size. But actually, we don't have to do that in this class because all the problems we met will satisfy those two conditions. Okay, so based on what we learned before, if those two conditions are satisfied, so we can use a normal model to describe the variability of p hat. And of course, we know that the mean of p hat, mu sub p hat, we know the mu sub p hat is equal to the population proportion, which is 0.5, as mentioned in the example, because we want to say if the real population proportion is going to be greater than 0.5 or less than 0.5 or equal to 0.5, whatever. But which means that in this case, the population proportion we're dealing with is 0.5, and of course, the standard deviation of p hat would be equal to the square root of p times 1 minus p over n. I mean n, not 1,000 in general. divided by n here. Since the sample size here is 1000, so that's why we have the sample standard deviation is equal to square root of 0.5 times 1 minus 0.5 divided by 1000, which is approximately 0.016. Okay, now once we get the mean, once we get the standard deviation, we can just draw the normal curve. So since p hat follows the normal distribution with mean 0.5, and of course variance would be the square of this number here, so 0.016 square. Okay. All right, so basically if we want to draw the normal curve, the symmetry was 0.5, and this number here would be p plus sigma p hat, so which is 0.5 plus 0.016, so we get 0.516. And this number, of course, would be p minus say 1 standard deviation of p hat, so which is 0.5 minus 0.016, which is equal to 0.484. So this is the normal curve of the p hat here. Now, before talking about before talking about how to conduct the hypothesis testing, I would like to introduce a new definition. It's called a p-value. So a p-value of first of all is the probability of observing the sample statistic as extreme or more extreme than one observed under the assumption that the statement in the null hypothesis is true. So in this case, we have, if we go back this example here, we have that the sample statistic over here is p hat, which is equal to 0.534. And based on the definition of p-value, we know that p-value is the probability of observing the sample statistic. In this case, is p hat is equal to 0.534 as extreme or more extreme than one observed under the assumption that the statement in the null hypothesis is true. So what does it mean? So I will say that 0.534 is somewhere over here, right? And we know p-value is the probability of observing the sample statistic as extreme or more extreme. So I would say in this case, the p-value would be equal to the probability that p hat is greater than 0.534. That's what does that mean by saying p-value is the probability of observing the sample statistic as extreme or more extreme than one observed under the assumption that statement in the null hypothesis. So basically, in this case, p-value is equal to the area of the shaded region here, which is equal to the probability that p hat is greater than 0.534. Okay, this is a new definition, and this is the pretty much the most important definition in the section of hypothesis test. So once we know the definition of hypothesis test, let's see how it works. If the probability of getting sample statistic as extreme or more extreme, then the one obtained is small. Then the one obtained is small under the assumption statement in the null hypothesis is true, reject the null hypothesis. So what does it mean? So this probability that talking about here is called p-value, right? So base means if this p-value is small under the null hypothesis, then reject null hypothesis. Okay, so that's what it's saying here. So if the p-value is small enough under the null hypothesis, then we're gonna reject null hypothesis. Why? Why is that? Let's just go back to this normal curve over here. So the p-value over here represents that p-value is the probability that the p hat is greater than or equal to 0.534, right? So that means if this probability is too low, if this probability is too low, that means the probability is too low to draw a sample with a sample proportion 0.534 or more bigger or more extreme from a population with a population proportion is 0.5. So that means the probability is too low to draw a sample like this from a population like this. Okay? If this happens, we're gonna reject this null hypothesis because it's pretty much not impossible to draw this kind of sample from this kind of calculation. From this kind of population over here. That's what I mean. So once again, if the p-value is too low, that means the probability is too low to draw a sample like this from a population like that. In other words, it is very possible to draw a sample like this from population with the population proportion like it's not equal to 0.5 or greater than 0.5 or less than 0.5, whatever. So there are gonna be different situations based on the different problems based on what kind of test we're doing. It could of course it could be two-tailed test or left-tailed test or right-tailed test, whatever. Okay, but the point I would like to emphasize over here is that if the p-value is too small, that means the probability is too low to draw a sample like this from population like that, and that's why we reject null hypothesis over here. Okay, I wish this makes sense to you. Once it does, let's just take a look at the logic of the p-value approach. So this pretty much the exactly same thing as what I just mentioned. A second criterion we must use for testing hypothesis is to determine how likely it is to obtain a sample proportion of 0.534 or higher from population whose proportion is 0.5. If a sample proportion of 0.534 or higher is unlikely or unusual, we have evidence against the statement in the null hypothesis. Otherwise, we do not have sufficient evidence against the statement in the null hypothesis. That's pretty much the same thing as what I just mentioned above here. So if the p-value is too low, that means it is unlikely or unusual that the sample we got here is drawn from the population with a population proportion 0.5, and that's why we reject the null hypothesis. That's why we reject the null hypothesis with the population proportion is 0.5. Okay, I wish that makes sense to you. And this graph is the same thing as what I just draw. So we can compute the probability of obtain a sample proportion of 0.534 or higher from the population whose proportion is 0.5 using the normal model. So basically, since it's a normal distribution, we can calculate this this probability, right? So first of all, we want to standardize this parameter over here. So z would be equal to p hat minus p over square root of p times 1 minus p over n. Okay, that's exactly what we got here. So this is I just rewrite it over here. Z is equal to p hat minus p over square root of p times 1 minus p over n. I'm not sure if you are still remember the standardization of normal variable or not. Z is in general, z is equal to x minus mu over sigma. So basically, if the variable minus the mean and divided by the standard deviation. So since the variable over here is a p hat, and we know the expected value of p hat is p, right? So which means this is a mu sub p hat. That's why we minus p here. And we know that the standard deviation of p hat is square root of p1 minus p over n. That's why divided by this down here, because it's standard deviation. And this whole thing is called a standard. This whole thing here is called a standardization. And then once we know the formula, we just plug the numbers back into the formula here. We know p hat is 0.534, p is 0.5, 0.5, 1 minus 0.5 divided by 1000, which is the sample size. And we have the corresponding z-score is 2.15. So then we're going to have the probability that p hat is greater than 0.534. This is equal to the probability z is greater than 2.15. So this is because z is equal to p hat minus p lower square root of p 1 minus p over n. And of course, we can get from this probability from either from the z table or from the calculator. So of course, if you have a calculator, you can compute this probability directly. But if you don't, you want to work with z table. Please remember, all the probabilities you get from z table is z is less than 2.15. And this would be equal to 1 minus that. You can get this probability z is less than 2.15 from the z table and subtract that from 1 to get the probability z is greater than 2.15. Okay, I wouldn't show you how to work with the z table because I have shown to you already. Of course, once again, you can get this probability directly from the calculator. But if you have any problems with the z table thing, please feel free to email me or just come to my office hours. Also, you can find the z tables on Canvas under the lecture notes, I guess. Now, once we get once we have the p-value, and as what I just mentioned here, if the p-value is small enough under the null hypothesis, we're gonna reject null hypothesis. But how small is small enough? How small is small enough? Let's take a look at it. What is down here? The value 0.0158 is called the p-value, which means that about 2 samples in 100 will give a sample proportion as high or higher than the one we obtain if the population proportion really is 0.5. Because these results are unusual, we take this as evidence against the statement in the null hypothesis. What does it mean by the results are unusual? We usually compare the p-value with alpha. If the p-value is less than alpha, then we're going to see the p-value is small enough under the null hypothesis, and then we're going to reject null hypothesis. So in other words, if p-value less than alpha, then reject null hypothesis. And the alpha is always given. Alpha is always given. And I wish you still remember that sometimes the value of alpha is given in the problem. Sometimes it's not given directly, but it's given indirectly at least. I wish you still remember that the level of confidence is equal to 1 minus alpha. So of course, alpha is going to be equal to 1 minus the level of confidence. Okay? Sometimes the problem gives you the level of confidence, you subtract from 1, get the alpha. And then you compare the p-value with alpha and see if it's greater than, if it's less than alpha or not. So if it's less than alpha, reject null hypothesis is greater than equal to it is very rare we will have a p-value is exactly equal to alpha. It's very, very rare. But I never met it. But you will probably meet it. But anyway, if you say something that p-value is equal to alpha, you do not reject it. Okay? So if p-value is less than alpha, reject null hypothesis. If a p-value is greater than or equal to alpha, do not reject it. Right? So I wish this is clear to you. Let's take a look at this. So what is talking about over here? So it says that if the probability of getting a simple proportion x extreme or more extreme than the one obtained is small under the assumption the statement in the null hypothesis is true, reject null hypothesis. So it's exactly the same thing. So if I just rephrase this whole thing here, that means if p-value, let me rewrite it, is less than alpha, reject null hypothesis. That's what it's talking about here, okay? So basically, once we know how to calculate p-value, and then we know that if we want to do the hypothesis testing for the population proportion, we know that z is equal to p hat minus p divided by square root of p times 1 minus p over n. Since we know that the p and n would be given, should be given in the problems, and we need to calculate p hat. So we know that the point estimate of p, the proportion of the population with a certain characteristic, is given by p hat is equal to x over n. So of course x is equal to number of individuals in the sample with a specified characteristic, and n is sample size. So we know p hat is equal to x over n. I think we learned this in chapter 2, I think. Chapter 1, chapter 2. And then we have this whole thing here. Actually, we have seen this whole thing in the previous slides. Let's just go over it again. So the same distribution of p hat is approximately normal. So with mean is equal to p, and standard deviation is this equal to this whole thing here. And provided the following requirements are satisfied, the sample is a simple random sample, and np times 1 minus p is greater than or equal to 10, and the sample values are independent of each other. So technically, we should check these 3 conditions, but in fact, we don't have to in this class, because pretty much all the problems we meet in this class are gonna satisfy those 3 conditions. All right. So basically, let's take a look at what's talking about here. To test the hypothesis regarding population proportion, we can use the steps that follow, provided that, of course, the sample is obtained by a sample random sample, and p hat p0 times 1 minus p0 is greater than or equal to 10. The sample values are independent of each other. So this is pretty much the same thing as what we mentioned. Okay, of course, the p sub 0 is just the p that given here. So basically, is the population proportion we're gonna test. Okay, or p hat is the population proportion that would be in the non-hypothesis. So once once this is clear, let's just take a look at how to conduct the hypothesis test for a population proportion. So first of all, you want to determine the non and alternate hypothesis. So if you want to do that, you want to see what kind of test we're doing here. Is it two-tailed test, left-tailed test, or right-tailed test? Okay. Of course, this p sub 0 is the assumed value of the population proportion. So same thing as what we mentioned in the lecture video 8.1. If it's two-tailed test, we're gonna have the p is equal to p sub 0 for the non, and p is not equal to p0 for the alternative. Okay, and for the left-tailed test, this is the equality. Of course, is the non, and we're gonna have p is less than p sub 0 for the alternative. And then same thing here. The non is always a statement containing equality, and since it's a right-tailed test, in the alternative, we're going to have p is greater than p sub 0. Okay, that's step 1, determine the non and alternate hypothesis. Now, step 2, select the level of significance alpha depending on the seriousness of making type 1 error. So basically, the value of alpha is always given either directly or indirectly. So the directly means that it's given directly means that you can find the value of alpha directly from the problem. It's given indirectly means that sometimes the problems give you the level of confidence, and we know alpha is equal to 1 minus the level of confidence, and that's how we find the value of alpha. It's very important because we're going to compare the p-value with the alpha. If p-value is less than alpha, we're going to reject non-hypothesis. So it's very important to find the value of alpha first. So once we find the value of alpha, and then we just need to go ahead to calculate the p-value. Okay, so we're gonna go over two different ways. One is by hand, one is by the calculator. So I'm gonna make a separate video for to show you how to find the p-value from the calculator. But in this video, I just show you how to calculate the p-value by hand. So basically, first of all, if we want to calculate p-value, we just need to calculate the critical value of z sub 0 first by this the whole standardization part. So just p hat minus p sub 0 square root divided by square root of p sub 0 minus times 1 minus p sub 0 all over n. So because we know that p hat is a normal distribution with mu sub p hat and sigma p hat square, right? So we got a mu sub p hat is equal to the population proportion, which is p sub 0 given the problem, and the sigma p hat would be equal to square root of p 1 minus p over n, and we know that p is equal to the p sub 0 given the problem, so it would be p0 1 minus p sub 0 over n. And then we know that z is equal to, in general, z is equal to x minus mu over sigma, which is the standard deviation. So this is how to standardize a normal variable in general. Okay, this is super important. That's why I just write it down again and again. So in this case, we have, of course, we're talking about the variable p hat, and mu is p sub 0. Standard deviation is the whole thing at the bottom here. Okay. All right. So once we find the z sub 0 by the standardization, let's take a look how to find the p-value based on the z sub 0 by the value of z sub 0. So we're gonna have different ways to find the p-value for the different kind of tests. So as what we mentioned in the last lecture video, we know that we're gonna have 3 different kinds of tests: the two-tailed test, a red-tailed test, and a left-tailed test. So two-tailed test means that p hat, not p hat, not p hat, is p is for the alternative, p is not equal to p sub 0. So this means that p could be greater than p sub 0, or p could be less than p sub 0. Okay, that means the p could be extremely large or extremely small. Okay, and we know that the normal curve is symmetry around 0, so the sum of the area in the tails is the p-value, and we know the sum of the area in the tails would be equal to 2 times 1 of the area, because symmetry and the area of those two regions are completely equal to each other. Okay. So that would be 2 times the probability z is greater than the absolute value of z sub 0. So the reason why we put the absolute value over here is just to make sure it's a positive. Okay. This is for the two-tailed test. This is for the two-tailed test. Okay. The p-value is equal to 2 times the probability that z is greater than z sub 0. Of course, you can get the z sub 0 from this formula up here. This is for the two-tailed test. And then let's take a look at the left-tailed test. Okay, the p-value would be equal to, since it's left-tailed test, that means p for the alternative, p is going to be less than p sub 0. So it's going to be all the way to the left. So the p-value is going to be equal to the probability that z is less than z sub 0. Okay, and similarly, the red-tailed test is the p-value would be the probability that z is greater than z sub 0. Okay, so you just need to, once you get the value of z sub 0, you just need to go ahead to find the p-value based on what kind of test you are conducting. So this is the p-value approach by technology. I'm gonna make a separate video for that. Let's skip it over here. So once we get the p-value, we just need to compare the p-value with alpha. If p-value is less than alpha, reject null hypothesis. Okay, and then state the conclusion. Okay, If reject null hypothesis, we're going to say that there is sufficient evidence to support the alternative. If we fail to reject null hypothesis, that means there is insufficient evidence to support the alternative. All right. I think everything's done here. Let's just take a look at how to do this hypothesis test in this example based on what we just went over. So it says that in 1997, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In 2007 poll of 1010 adults nationwide, 525 stated they did not trust the media, and the alpha is equal to 0.05 level of significance. Is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997? Okay, now if we wanna test if the population proportion has increased or not, first of all, we want to set up the non and alternate hypothesis, right? And of course, the p sub 0 over here is equal to 0.46. That was the old population proportion. So in this case, the non-hypothesis would be p is equal to 0.46 versus the alternative. Now, what kind of test we're doing? Since we're testing if it has increased or not, so it would be a red tail test. So p would be greater than 0.46. Okay, that's step 1. Step 2, what's the value of alpha? That would be 0.05, right? And then we want to calculate the test statistic. Z sub 0, we want to calculate p hat first. P hat is equal to, of course, x over n, which is 525 over 1010. This is pretty straightforward. And then z sub 0 is equal to p hat minus p sub 0 divided by square root of p sub 0, 1 minus p sub 0 over n. And we know p hat is 525 over 1010 minus p sub 0 is 0.46, and then divided by square root of 0.46, 1 minus 0.46, divided by n. What is n? N is the sample size is 1010, right? It's 1010. Of course, you type the whole thing in your calculator, you will get this would be equal to 3.83. Okay, I just copy the answer from the solution. Okay. All right, and since we are doing a red tail test, we got the statistic. We're going to have to find the p-value, right? So the p-value is going to be equal to the probability z is greater than this z sub 0, which is 3.83, right? Why is it greater than? Because we are doing the red tail test. Of course, you can always find this probability from whatever calculator from z table. Okay, we wouldn't go over that. So from the z table, this probability is approximately. Yeah, this is approximately. Let me rewrite it. This is actually approximately equal to 0. Okay, since 0, of course, is less than 0.05, right? P-value is less than the alpha, then the conclusion reject h sub 0. There is sufficient evidence to support that. What is that again? That P is greater than 0.46. Okay, or you say that the percentage has increased. So basically, that's pretty much the whole thing you want to show to get the full credits, whatever on the homework or on the test. That's the whole procedure, okay? That's the whole procedure. So of course, that's how you do it by hand. That's how you do it by hand, okay? Of course, you can, if you have a TI-84, TI-83, you can calculate, you can get the p-value from the calculator directly. So yeah, in that way, you can skip this part. You can skip this part. If you are able to find the p-value from the calculator directly, you can skip this this calculating test statistic over here, okay? But you gotta show me this, and this, and the conclusion to get the full credits. Of course, if you don't have the calculator, you should show me all those 5 steps here. All right, so that's pretty much how we do it. And let's take a look at the solution here. That's pretty much the same thing as what we got above here. So actually, technically, we check those 3 conditions, but we don't have to in this class. So we just skip it because they're always satisfied. So first of all, alternative, the non and alternative. So P is equal to 0.46, and then P is greater than 0.46. This is red tail test. And then alpha is 0.05. Symbol P hat is equal to 525 divided by 1010, which is 0.52. And then we just go ahead to calculate the Z sub 0 by the formula of standardization, which is equal to 3.83. So once we got that, we know the p-value would be equal to the probability Z is greater than this test statistic, which is 3.83. So p-value is approximately 0, which is less than alpha. So, oh, I'm sorry. So if the p-value is less than alpha, then we reject null hypothesis. So don't forget to say that reject null. There's sufficient evidence at the alpha is equal to 0.05 level of significance to conclude that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997. So basically the same thing as what we got here. So there is no sufficient evidence to support that P is greater than 0.46. And that's pretty much how to conduct the hypothesis test for the population proportion, and I wish it makes sense to you, and I'm gonna make a separate video to show you how to find the p-value, from the calculator. Okay, all right, that's pretty much all about this video.